Hi. Welcome back to our channel Tech. Please don't forget to give your feedback after watching this video. We also request you to subscribe our channel and press the bell icon to receive notifications. In this video, we will learn about the VI characteristics of the diode under forward and reverse biased condition. The response of a diode when connected in an electric circuit can be judged from its characteristics known as volt-ampere, commonly called VI characteristics. Let us see first the VI characteristics of the diode under forward biased condition. The figure shows the circuit arrangement for IN4007 forward biased diode and the forward characteristics. In circuit diagram we have the regulated power supply with the range of 0 to 30 volts. By adjusting this we can increase the forward voltage of the diode. The graph of forward current against forward voltage across the diode is called forward characteristics of the diode. Basically, the forward characteristics can be divided into two regions. That is region O to P and P to Q. In region O to P, as long as the forward voltage is less than the cut-in voltage, the current flowing through diode is very small. It is assumed as zero practically. In region P to Q, if the forward voltage increases beyond cut-in voltage, the depletion region becomes very thin. The cut-in voltage is 0.3 volt for germanium and 0.7 volt for silicon. We can observe that the exponential increase in the forward current or diode current. The point P after which the forward current starts exponentially is called knee of the curve. The forward current is the conventional current, hence it is treated as positive, and the forward voltage is also treated as positive. Hence the forward characteristics is plotted in first quadrant. The resistance offered by the PN junction under forward biased condition is called forward resistance. It is defined in two ways. One is DC or static forward resistance and another one is AC or dynamic forward resistance. Static forward resistance is defined as the ratio of the voltage to the current in the forward bias characteristics of the PN junction diode. The DC or static resistance at the operating point can be determined by using the corresponding levels of forward voltage and forward current as shown in figure. That is, RF is equal to V by I. Here, the DC resistance is independent of the shape of the characteristics in the region surrounding the point of interest. The DC resistance levels at the knee and below will be greater than the resistance levels obtained for the characteristics above the knee. Hence, the DC resistance will be low when the diode current is high. As the static resistance varies widely with 5 and 1, it is not a useful parameter. Now let us see about AC or dynamic resistance. It is defined as the reciprocal of the slope of the volt-ampere characteristics. It is represented as RF is equal to change in voltage, divided by resulting change in current. That is delta V divided by delta I. A straight line drawn tangent to the curve through the quiescent point or Q point as shown in figure will define a specific change in voltage and current which may be used to determine the AC or dynamic resistance for this region of the diode characteristics. As shown in figure, for a small change in voltage, there will be a corresponding change in current, which is equidistant to either side of the Q point. Hence, the AC or dynamic resistance is determined as RF is equal to delta VF divided by delta IF, also equal to inverse of slope of forward characteristics. Generally, the value of forward resistance is very small, of the order of few ohms in the operating region above the knee. Now let us discuss the reverse characteristics of the diode. The figure shows the circuit arrangement for IN4007 reverse bias diode and the reverse characteristics. In circuit diagram we have the regulated power supply with the range of 0 to 30 volts. By adjusting this we can increase the reverse voltage of the diode. The graph of reverse current due to minority charge carriers against reverse voltage across the diode is called reverse characteristics of the diode. Please note that the polarity of the diode is opposite to that of forward biased diode. Hence in practice the reverse voltage is taken as negative. Similarly, the reverse current is opposite to that of forward current. Then it is also taken as negative. Hence the reverse characteristics is plotted in third quadrant. The minority carriers, electrons in the P region and holes in the N region, wander over to the junction and flow towards their majority carrier side, giving rise to a small reverse current. This current is known as reverse saturation current. The magnitude of reverse saturation current mainly depends upon junction temperature because the major source of minority carriers is thermally broken covalent bonds. The reverse voltage at which the junction breakdown occurs is known as breakdown voltage. Please watch the video number 11 to know the concept avalanche and Zener breakdown. Please note that forward current is in milliamps and reverse saturation current is in microamps. The point where breakdown occurs and reverse current increases rapidly is called Ni of the reverse characteristics. Next we will discuss about the reverse resistance of the diode. The PN junction offers large resistance in the reverse bias condition called reverse resistance. This is defined in two ways. That is reverse static and dynamic resistance. The reverse static resistance is ratio watt applied reverse voltage to the reverse saturation current. And the reverse dynamic resistance or AC resistance is the ratio of incremental change in the reverse voltage applied to the corresponding change in the reverse current. The dynamic resistance is most important in practice whether the junction is forward or reverse biased. Finally, this is the complete VI characteristics of the diode. Thank you for watching and subscribing our channel. Also we request you to share this video to your friends. Happy learning!